Good afternoon, ladies and gentlemen. Yes, let's switch to the English. Let's begin the session 4. We're going to talk about the expectation of 5G core technology. And today, the November 19th, 2020 is a very important date. We're going to start talking about the 6G, which will be deployed approximately 10 years from now. So I hope that the audiences are very excited about the bright future that has been proposed by the government and the industry and the 5G vision of the 5G forum. So we're going to talk about, but those bright future can only be possible by solving various technical problems. So we're going to hear what technology are going to be developed to fulfill these requirements and to make the bright future of the 6G. So we have 6 talks, and then we're going to hear the core technologies. I'm sorry, I forgot to mention who I am. This is Seongjun Oh. I'm a professor at Korea University, and I'm also a co-chair of the 6G task force of the 5G forum. Okay, so the first one is from the Professor Mehdi Bennis of University of Oulu of Finland, and he's going to talk about the extreme, ultra-reliable, low-latency in communication, URLLC. URLLC has been defined in the 5G, and then I hope that that will be more developed in terms of the extreme URLLC in 6G. Let's please join me. Welcome, Professor Mehdi Bennis.
So here is the outline. First, I'll discuss 5G URLLC and some of its current limitations. Before I move on to the gist of the talk, which is about extreme URLLC, so I'll motivate the vision and challenges and enablers while selecting some vertical. Then also present just some results here and conclude the talk. All right, so first let us start with URLLC and some facts. So what we know today is that URLLC is in fact the statistics of extreme and rare events, where the goal is to characterize and tame the tail distribution of a probability distribution function. This could be your latency, it could be throughput, or any other key performance indicator. And for this, from a theoretical perspective, we looked at it using several mathematical tools such as extreme value theory, value at risk, and others. And typically the key performance indicators here are packet error rate, system failure rate, survival times, and others. Now, from a TraceGPP perspective, of course, where the goal is pretty much the same, but the focus here is on using system-level simulations to gain insight on the results. Okay, so here TraceGPP has done a great job in terms of coming up with several enablers, such as changing the numerology, and then of course coming up with the graph-free transmission, especially in the uplink, and a number of techniques such as of course time, frequency, and special diversity techniques. But again, the focus here has been on communication reliability, because I will come back to it later. Just a few takeaways here, of course. So 5G URLLC, I mean, the gains behind, ultra low latency and high reliability usually come at the expense of sacrificing spectrum efficiency, right? I mean, this is, in order to ensure reliability, well, you retransmit your packet a number of times, or you need to basically allocate more transmission points, as in multi-connectivity. So you need to sacrifice spectral efficiency, and of course energy. This goes hand in hand, and sometimes you need to over-provision resources in terms of resource blocks or high transmit power. The assumptions here has been so of course the focus has been on sparse deployment, and meaning not so dense. And pretty much the environment is controlled, right? These are not, say, uncontrolled environment where with harsh propagation and so on and so forth. Although that is, of course, now changing. And as you can see on the right, of course, that when 5G came, the breakdown between EMBB, URLLC, and MMTC was actually a zero-sum game. But now we see that that this is changing and the boundaries are being blurred. For instance, virtual reality application may require not only EMBB but also URLLC. Likewise, for robot requires EMBB for vision, but also URLLC and even MMTC. Okay. All right. Now, of course, in 5G URLLC, ensuring reliability when you have plenty of when you have no issue with the model is relatively easy. Now things become more difficult when we don't have access to models. This is precisely the current focus of statistical and predictive URLLC, because in fact this tail distribution is not given a priori, and it has to be learned typically based on samples. This could be your channel samples, it could be your latency samples, or other data distribution that you may have. So to solve this problem, typically this can be cast as a machine learning problem. So reliability has to come hand in hand with sample complexity, because now the reliability that you need to ensure is going to be a function of how many samples you have for learning the distribution. By learning, I mean here you need, of course, to train your distribution, which is a separate subject on its own. But yeah. So this brings in machine learning, of course, to the picture in terms of, is it data-driven approaches or model-driven or hybrid, when you actually have some prior information here from your environment or even from the application. But typically the questions as seen here is how many samples you need to learn a model for a given target reliability, while being robust to, of course, the model phenomena, but also unmodel phenomena. And this is where, in fact, machine learning may be even more helpful. Okay. Now, as we know, machine learning is all about generalization. So this is also key here in the realm of URLLC. Also, control stability is key, especially when talking about cyber physical control systems, and I will come back to that later. So there are a lot of trade-offs to be studied. And still within the realm of cyber physical control systems, these are, of course, very important in beyond 5G and even towards 6G. When we talk about centralized control or collaborative control, human control collaboration. Here again, the same problem is, can you control an object or robot when you don't have access to a model, right? So, which means you need to do it from data. So again, this brings in the whole notion of sample complexity, robustness, control stability here are key measures going beyond communication reliability. Okay. And this brings in an important component of the co-design between communication control, which is part of this extreme URLLC vision. Right. So in fact, what we have is we have two extremes that are emerging. On the one hand, you have the quest for taming the tail distribution and going for 9 nines and even more. And on the other hand, we also should start maybe asking the question: can we relax some of this communication requirement? Because now, if you talk to KUKA or other robotics companies, in fact, they will tell you that what they care about is, in fact, system stability or the failure of their system when 3 packets, consecutive packets, are lost, or 5. Okay, they don't care about 1 packet with a given communication reliability. Okay, so packet error rate for them is meaningless. The focus is whether I receive reliably 3 packets or 5. Okay, so this actually allows us to now to revisit URLLC from a different standpoint, meaning can we relax this reliability measure by instead focusing on control stability or control safety. Okay, so this brings us to the vision of extreme URLLC, which is actually broken down into 3 aspects. So you have the first aspect, which is on the bottom part here, called URLLC, I mean predictive URLLC, you can say, but also includes, of course, TSN and other efforts in that regard. Then we have on the left what I call non-RF. This is actually an important aspect where we need to use different modalities in order to predict more reliably and maybe achieve those 9 nines. Okay, because sometimes your data carries no statistical relevance, so one needs to now go for different modalities, and among them here Of course, is vision. So we could use RGB depth cameras, LiDARs, thermal sensing cameras. And the question, of course, here is how do you fuse these modalities? Because sometimes having more modalities is not really the way to go about it. But this is a fundamental problem in its own. And then you have on the top right, you have this COCOCO, which is communication and control co-design, which I just stressed. This one comes with its own requirements of stability, controllability, observability of robustness. This is, in other words, when control theory meets machine learning, but also communication. So there is a lot of interesting aspects in this. So let us move to the first use case, which is the application of federated learning in vehicular communication. Here the problem is as follows. Every vehicle wants to minimize its transmit power subject to the network-wide latency. This is a challenging problem because we need to basically characterize the tail distribution of the network-wide latency, which the vehicle does not have access to. Therefore, there are two solutions. The first one is that the vehicle estimates locally this distribution. However, the latency requirement will not be satisfied. Or the other case is that the vehicle relies on the roadside unit to essentially estimate this distribution and then broadcast it back to the vehicle. Instead, what we'll be doing is use federated learning, in which the idea is that every vehicle, instead of transmitting its raw data, will transmit the model parameters of this Pareto distribution. And then the roadside unit will basically average all these models and then send them back to the vehicles. And this, of course, iterates until convergence. So this is essentially what we did. In terms of results, what we can actually see is that the proposed federated learning solution not only communicates less in the uplink, since it only transmits the model parameters, but also achieves the same reliability as the centralized case, which is based on transmitting all the raw data from the vehicle to the roadside unit. Okay, now let us move to the non-RF part. So again, here, as I motivated before, extreme rare event prediction based on RF only data or modality sometimes is actually insufficient. Even if you have 1 million sample, maybe those samples are actually not informative enough. Okay, so the idea here is to leverage other non-RF modalities and see how we can basically predict better, for instance, the blockage of a channel. Okay. So obviously, if we use cameras, then there are some assumptions such as line of sight, which has to be ensured. But again, we can overcome that by deploying multiple cameras for line of sight. But we could also use, I mean, even RF sensing is obviously a very interesting aspect in 6G or beyond 5G. This is not the focus of this presentation. So again, we can use RGB depth cameras, LiDAR, radars, hyperspectral imaging cameras, and so on and so forth. In terms of use cases or applications, actually, any possible use case can be studied through this non-RF components. Okay, so there is the millimeter blockage prediction, which I will present to you in detail next. There is, of course, predictive mobility, handover, robotics control, swarming, platooning. I mean, visual AI. This is on its own very important research thrust that deserves more research. Okay, so let us move on to an application of visual sensing as an URLLC enabler. So here again, the motivation is the same. And actually, I want to visit this problem of blockage prediction. I mean, this is a problem which is discussed, studied in great details, but still we don't have a good grasp of this. I mean, of this channel, because in fact we don't have model for that. Okay, so TraceBB has a number of models, but now here the goal is we want to learn based on data. Okay, and of course using the camera. So this is what we have. I have this base station, and I have communicating to its user. And then you have a blocker here, which is a pedestrian, but you could also be a vehicle, could be anything else you want. Okay, and essentially we want to see whether we can predict this drop of received power or SNR or SINR, which happens actually very suddenly and doesn't last that much, in fact. Okay, but are we able to predict it? So the idea would be to use these RGB depth cameras where we would fuse the RF and non-RF modalities, okay, as I said before. How to do that? Typically you cast this as a time series prediction again, and then you can, if you combine images, of course, then you have to resort to convolutional neural networks. So here this conv LSTM refers to that, but you could also combine it with your RF base, which is power, and this is also can be modeled as a time series prediction, and you can combine both, obviously. So now, how do you transform one modality? I mean, the non-RF to the RF one can be cast as a transfer learning problem. I'm not gonna delve into this, but just worth mentioning it. And again, yeah, what architecture you take and so on and so forth. This is not the goal of this talk. Okay, and then what we can do, in fact, I mean, the idea is to take, so every camera will take consecutive images of, okay, of the target, of course, of the blocker, okay, and start to build a data set. And this is a supervised learning, so we have the ground truth, meaning that every image will be associated received power. Okay, and then what we do, we would feed this data to our convolutional neural net or LSTM or any other favorite neural architecture, and train it, and essentially try to now build a model and test it. Okay, so now training the model is one thing, but of course you can use it now to help you predict, I mean, that the signal will drop, and then you need to reassociate the user to a different cell. Okay, this is one use case. But essentially, visually, this is what we get. So on the left-hand side, you have we have two figures. The one on the left actually shows you what happens if you don't use the camera. So here you would actually wait until the signal drop before you trigger the handover. So this is a more of a reactive approach versus a more proactive approach, the one on the right, when actually you want to trigger the handover earlier, much earlier. And how would you do that? You would use the camera to help you do so. Okay. Now, if we zoom in now a little bit more, we have three baselines essentially. We have the baseline number one, which is based on the RF. This is the current one that we use. Number two is when we only use images to predict, and number three is when you combine images and RF. Okay, so essentially these are the three baselines we have. So if we now take the case when we combine the camera and the RF, so this is just a zoom out actually, also, or a zoom in picture of what we actually did. So essentially what we want to do is, if you have a camera, okay, we should picture it here as this millimeter wave UE, but actually it's a camera, which is going to be taking images, raw images, okay, and then we'll be transmitting those images to the base station, and then the base station would receive it, and then this is going to be serving as an input alongside with the RF data that the base station has, and then it would actually train the model. Okay. So the question here is, we were asking is, in fact, since these images can be heavy in terms of payload, what if we can try to compress the output of that image before feeding it to the base station? So essentially, this is what we did, because this actually allows you to trade off a bit of accuracy versus compression or communication. Okay, so this is what you can see here. The idea is, the higher the pooling dimension of the convolutional neural net, the lower the communication payload is. Okay, so you can see here you have the raw images. And as you play with the output of the filter, you could actually go from 1, 1, 4, 4, and even to 1 pixel, okay, which is 40 times 40, which is the dimension of the filter. So what we can see on the left-hand side, this is basically showing that, I mean, it plots the test performance in terms of root mean square error. And in x-axis is the communication cost for inference. So obviously what we can see here is if you want to reach very high accuracy, then you need large communication bandwidth, right? Versus if you want to really transmit something much smaller, then of course you get more error in terms of training. But interestingly, what you can see here is, in fact, even the 4040, which is a 1 pixel, if you combine it with the RF, it can still outperform the RF only prediction, which was actually interesting. Moreover, for people who are concerned with privacy issues, you can see actually the 1 pixel here, which just shows you basically if it's white, gray, and black, can serve as a kind of side information to help you predict much better than if you only had RF data. Okay, so now let us move to control, which is the third component of this extreme URLLC. So again, here, I mean, control is now prevalent, right? It's in the factory floors in terms of sensors, actuator controllers. It's also in drones, vehicles, automated guided vehicles in a factory. It's essentially an important component here. So now, in order to study this control problem, we need to do it jointly with communication, right? This is what I was saying before, that we need to look at the co-design of communication control. If we only look at communication, reliability, packet error rate, disregarding stability of the control and safety of the control, essentially it's not only suboptimal in terms of performance, but actually is not how robotic application works. Okay, so. So here again, I mean, there's a lot of work in control. Obviously, this is dating from the 60s or even earlier. But so stability is very well understood. But when you have a model, okay, so you have model predictive control, which is widely used actually in factories today. The problem is what happens is when you don't have a model. Okay, so this is what we call model deficit. Now, of course, as you may guess, is now we need to basically try to stabilize a control system based on data. Okay, but then how many data points do I need to be able to control my plant or my robot, right? And moreover, we cannot use black box machine learning approaches here because essentially we're dealing with stability. Okay, this is the stability of a flying drone. This is stability of a plant, right? So this is something which is very important. We need to pay a close look at it, right? So this generalization, machine learning versus stability is key. Perhaps we would go for more stability than generalization, okay? As opposed to a classical machine learning, which aims at higher generalization. And then, of course, now even for a problem such as remotely estimating a dynamical system, right, over wireless. So now this is I mean, if the wireless link now is intermittent and blocked, remote. I mean, this would impact obviously the remote estimation of this state, which in turn impacts the actuating, right? So this is something which is now currently being looked at various groups, including mine. But what I want to do here, for the interest of time, is just to show you, in fact, another problem which arises in control system, which is algorithm deficit, right? So here what we have the swarm UAV path planning problem, where we have a number of UAVs which we want to dispatch from source A to a destination, okay, B. I have a lot of drones here, and they are fully autonomous. Okay, so this is the setting. So these drones need to fly to their destination in, in an energy efficient manner, and without causing collisions to the neighboring drones. Okay, so essentially this can be, and moreover, we have of course disturbances in terms of wind. So you have the wind dynamics, which is actually disturbing the trajectory of the drone. In other words, this can be cast as a control problem, more specifically as a mean field control problem for controlling the drone. So I mean, I have put this a quick formulation here. Essentially, what you have a minimizing the cost function of a single drone. Subject to its own state. So the state here could be location, velocity, acceleration, plus some disturbances coming from the noise. And here the coupling among drones actually is not in the state, but is in the cost function, because it also depends on the neighboring drones. Okay, so you can see here the collision avoidance is what actually couples the drones, but also the connectivity, because they need to exchange some either state information or a model. So how would you basically solve this problem? Well, you need to write down the two-coupled partial differential equations that you can see here. One is called the Hamiltonian-Jacobi-Bellman equation, which is actually responsible for solving the optimal control for the given drone. And then the second equation, which is the mean field equation, which is called also Fokker-Planck-Kolmogorov equation, which is actually going to give you the probability density evolution of the population. Okay, so to break it down simply, the first equation is what would be for a given, say, a bird, and then the flock of the bird is given in the second equation. Okay. Now, without, the reason I put the equation is not to actually to go through them, but just to show you that actually this is an intractable equation which cannot be solved in closed form. Okay, so the model predictive control cannot be used here. So what we do, we actually resort to machine learning. So we try to approximate the first HGB equation and the second one, the FPK equation, using a neural network. Okay, so this is what we actually did, and we try to solve the problem. So this is a purely data-driven regression problem. So then you have this HGB learning control on the left. So here, this is a baseline where the drone will exchange at every time t it stays with each neighboring drones. So of course this is not feasible, but we just took it as a baseline. And then our proposed approach, which is called mean field game learning control, where here actually the drones will only exchange initially their state, and then on their own will actually estimate not only their optimal control, but also the population dynamics in a totally distributed way. Okay. So this is what we get. So the first row here, this is it's actually showing the trajectory of the drone for 30 seconds, 60 seconds, 90 seconds, 120 seconds. And the HGB again is the baseline. So and the proposed approach is the third one, the third row in mean field game. So as you can see here, in fact, what I want you to see is if you look at those trajectories, you can see that actually there are stars. So these stars actually capture the collision between the drones. So as you can see here, when you go from 30 seconds to 120 seconds, then you can see how many collisions happen between the drones when they're reaching the destination. However, in the proposed approach, you can see that there is actually zero collision, but the price to pay is in fact that the drone has to exert more control, meaning that he has to pay a price in terms of energy. So this, but you can see why it's a rather more circular trajectory than a kind of direct path from the drone to the destination. Okay. Again, and again, yeah, on the right hand side, this is just the convergence of the weights of the training algorithm. So here we just use a classical neural network to actually train our train our model. Since again here we're dealing with stability of the control, so here it is a swarm stability of the flock of drones. We had to, of course, make some assumptions in terms of normalizing the weights of the neural network, otherwise it actually diverges. So there are some issues here that has to be dealt with to make this solution work. All right. So this brings me to the end of the talk. Just a few conclusions here. So first of all, the long tail problem is fundamental issue in ultra reliable low latency communication, especially when learning from data. Number two, ensuring high reliability requires a number of modalities, so RF and non-RF. Number three, the co-design of communication control is essential, as opposed to treating them separately and looking only at packet error rate and communication reliability. And number four, edge AI and AI in general is a key enabler for ensuring low latency and high reliability. Finally, I invite you to check the vision paper with all the details included. Thank you very much.
For his nice presentation. The URL, he talked about the URLLC. URLLC is one of the three usage scenario for IMT 2020, the 5G IMT system. And then there's no doubt that the URLLC is a major application for the 6G. And then he proposed a nice direction how the URLLC can be developed in terms of by applying the machine learning and AI.